All right, good morning. Oh, gotta unshare my screen. Hold on a second. There we go. All right, how's everybody doing? Good, good, good. All right, so let me start by talking about the midterm a little, because I'm getting some questions on that. So, midterm will be this Friday. It will be a Canvas quiz. It will be given during class time, so it'll start at 11. It'll end at 11:50. It will be fill in the essay style questions where you're basically typing in text for the answers. The questions will be a combination of some short answer stuff, maybe, but mostly it's going to be programming questions. Some Bash, some C. Very similar to the one-day programs you've been doing, the homeworks you've been doing. If you've been keeping up with the ODPs, if you're able to do the ODPs and the homeworks and those make sense to you, and if you've been working more or less exclusively from the command line in a Linux environment, you should be fine. Okay, if I ask you about Linux commands, it should be things that you've been doing from the beginning. Moving around the file system, editing, compiling, making directories, things like that. Okay. I'm going to strongly recommend that while you're taking a quiz in Canvas, which is a 15-minute process, you don't be typing your answers directly into Canvas. The reason being that, like all web pages, there's lots of things you can do to inadvertently get yourself kicked out of the page. For example, some people use the tab key when they write code. If you're typing code into Canvas in the text entry spot, and you hit the tab key twice and start typing and hit a space bar, you might accidentally trigger the cancel button on the page, and your whole quiz entry that you've been doing goes away, right? So here's what I'm going to suggest. When you're taking an online quiz, right, type your answers into whatever your favorite editor is, okay, Notepad or VI or whatever, and then copy your code from there and paste it into Canvas to actually turn it in. And then if something goes wrong, if your internet connection goes down, if you hit the backspace key and it takes you out of Canvas or something, right, you go back into the quiz, you take your answers, you paste them again into there, and you submit them. Okay, so don't get to 11:49 and get ready to hit the submit button and get a message saying, Canvas has logged you out, please log in, and you have no copy of your work. Okay, so do the work on your favorite editor, copy and paste it from there into Canvas, just in case something goes south. Not sure what else I can tell you about the midterm. I haven't written it yet. I'll write it in the next few days. But like I say, mainly programming questions, some Bash, some C. Some of the questions will ask you to write an entire script or a complete main program. Some of them will ask you to write a function or a few lines of code. Okay, if you're in doubt, ask. But pay attention to what the question is actually asking you to do. I'll be online in the regular Zoom classroom, so you can chat to me on a private chat if you have questions. I'll also be keeping an eye on my email. So if you can't get into Zoom or something catastrophic happens, right, send me an email right away and let's figure it out. So that'll be Friday during regular class time, and there's no lecture scheduled for Friday. All right, few comments on homework 4. So homework 4 looked really good. Most people had a game that successfully played, 20 sticks, did the right stuff for the actual gameplay. Most of the point deductions were the details, right? And we talked about a lot of details when we were going over the assignment and looking at the sample code. Details like if the person puts in more than one command line argument, print a message and exit. If the person puts in one command line argument, it better be a legal number of sticks. If it's not, print an error message and exit. If you ask the person how many sticks to take and they don't put in a valid answer, ask them again and keep asking them, and don't give up after 2 tries. So those kinds of details, lots of deductions for variations from those. And the reason I'm considering those things in the grade is because, again, right, part of the goal here is to get better at following an assignment prompt and being able to tell if your code satisfies the requirements. And this gets more and more important as you go further and further in schools, so we want to get some good practice on that. So I graded the assignments, posted grades, posted comments in the comments section on Canvas. If you have any questions or concerns about those, let me know. If you didn't get your code figured out, or you can't figure out how to get it to a point where it would, get full credit, come by office hours. We can screen share. You can show me your code. We can work on it from there. Okay. We're not going to write another version of 20 sticks. Okay. But it's important to know how to make this work both in Bash and in C, because these are skills we're going to build on, right? Being able to parse input, things like that. Also, there's cases where I saw things in code that did not cause problems in this case, but might cause problems in the future. For example, uninitialized variables. Well, sometimes you luck out, and an uninitialized variable is not between 1 and 4. In fact, most of the time it's not. And so if you're not checking the return value from scanf, you might luck out. If the person puts in an illegal entry, maybe it converts to some bizarre number and your code says that's out of range, right? But you always want to check the return value from scanf. You never want to use scanf, okay? Most people who did got lost points because their code would go into an infinite loop if a bad input was put in. So keep those things in mind, and I made comments on those where I noticed them. So flow charting and pseudocode can be helpful here. So for example, for our stick program, right, you've got to write your main program with a pair of arguments, an integer and a char star star. And remember, argc is the number of arguments, and argv is the array of arguments. So if the person, let's say your executable is called stick, if they say stick 23, argc is 2. And argv bracket 1 is the string 23. If they say stick ha ha, argc is 3. Right, because they're stick ha and ha. And argv 1 is the first ha. Let's make this ha ha. And argv 2 is ha ha. And if the person just says stick, then argc is 1. And in all these cases, argv bracket 0 would just be stick, the name of the program. All right. So what does this do for us? It tells us that in order to know whether the person ran the program like this or like this or like that, the first thing to look at is argc. Right? We can't look at argv bracket 1 to see if it's an integer, because if the person says stick, argv bracket 1 is null. And if we try to run that through scanf, we're going to get a seg fault. I didn't see any seg faults in any of the code. That was so cool. Right? So we want to check argc before we do anything else. And so our pseudocode for our program, for the initialization of it, and I think we did the same code last week, might be something like this. If argc is bigger than 2, print an error message and exit. Because they can either say stick or they can say stick followed by a number, in which case argc would be either 1 or 2. So if it's bigger than 2, they put extra things on the command line. That's an immediate error. Just exit. If argc is exactly 2, then they said stick followed by what hopefully is an integer as that second argument, and that second argument is in argv bracket 1. So parse argv bracket 1. If it's not an integer bigger than or equal to 10, print an error and exit. Else play the game with that many sticks. Alright, if argc is equal to 1, and this is the only other possibility, argc is never 0. If it's not bigger than 2, if it's not equal to, it's got to be equal to 1. So we don't even really need an if here, but maybe just an else, right? So if argc is 1, ask for a number of sticks to play with. If not an integer bigger than or equal to 10, print an error and exit. Else play with that many sticks. And then we have the loop with user turn and computer turn, and loop until the game's over. Right? So the startup section, right, by writing this out in pseudocode, a flowchart or something high level like this, right, before we start writing code, we can see some things. For example, we can see that this business of if not an integer bigger than or equal to 10, exit, gets done twice. And maybe that's a good thing to throw in a function. People did a lot of putting things into separate functions, and that was fantastic. Okay, this is right where you want to be with coding. Breaking things into separate modules, right, and then pulling those together. So most people, if they were doing this, they made a function called, you know, parse sticks or something like that. So that was really good. That's going to help down the road too. All right. So the general flow of the program is, you know, check some condition, and if this happens, possibly exit. Check this condition, and if this happens, parse this and get some number out of it. Check this condition, and if this happens, get some number out of parsing. And then in either of these cases, that number that we got, that's the number of sticks to play with. Right? So if this parse gets thrown into a function, right, I'm going to save both of these in number of sticks, and then I'm going to go ahead and play the game. This is another thing. I saw some code where people used variables like I for the number of sticks, J for how many sticks you wanted to take, N for a 0 or a 1 indicating whose turn it was, and K for a flag to say if somebody had won the game. Right? I didn't see that, but it's an example, right? This is hard to code. It's really hard to debug, right? Number of sticks remaining, number of sticks to take, current player turn, winner flag, right? If you call your variables that, you're not going to get confused and accidentally check the player turn when you mean to be checking the winner flag, right? So don't be afraid to use good variable names, or names that make sense to you. And if you do this from the right, this is not something you do at the last minute to make your teacher happy, right? Change all your I's to number of sticks to play with, and so on. You do this in the beginning when you first start writing the code, so that as you're writing the code, you're avoiding mistakes where you're confusing variables, right? So just habits to get into. All right. So questions on any of that stuff? Questions on homework 4 or command line processing or anything like that? Oops. All right. I posted a link on Canvas. I mentioned this last week in class also. A link to an additional textbook that you can use for this course. So this is a PDF you can download from a link through Canvas. It's a really short book. It's not something I recommend you read cover to cover, but it can be a perhaps useful reference for some of the things we've been talking about and that we're going to talk about around C programming. So all of this business of reading input from the user and parsing it, and the idea of breaking those into 2 steps instead of just using scanf to combine them, that's all spelled out in here, right? It's an 8-page chapter. It's not a lot of text, but it's another presentation of some of these ideas we've been talking about, right? The idea of taking an input and then analyzing it using scanf, and how to deal with return values from that, and so on and so forth. We're going to talk about string processing probably next week, leading into a future homework assignment. So dealing with strings, taking them apart, putting them together, stuff like that. State-based programming we won't get into this quarter probably, but we probably will in winter. Pointers, so we're starting to talk about, you know, char star and eventually int star and ampersands, and of course char star star argv. So there's some information about those things in here. Bit flipping and recursion are more in 222, but if you've done engineering 270 with me, we talked about bit flipping, basically bit masks and anding and oring with bit masks and so on. That comes up in C a fair amount, especially when you get down to system level programming and you're dealing with device drivers and things like that. You'll do a lot of bit flipping. What I want to talk about this week includes splitting files up into multiple pieces and then putting them together with make files. And so there's some reference material in here on make files, and this is stuff we'll be talking about. And these last 2 chapters, gotchas and comments on coding style and stuff. When you have some downtime and you feel like just kind of flipping through this, take a look at this. Okay, these are sort of general ideas on things like coding style. Why do we want a coding style? What are some of the different ways that we can write if statements or function declarations and so on? You want to find your own style, okay, for sure, but sometimes it's useful to see different examples of the way people format their code and find something that you know works for you. Discussions of commenting. So I did not take off points for commenting on this assignment. I told you I wouldn't. But it looks like a lot of people could do a lot more commenting, and so there's some discussion in here on you know what constitutes useful commenting versus just commenting for the sake of having comments. And the gotchas talk about things like what can happen if you start nesting your curly brackets too deep, right? And we looked at this a little bit last week. If you don't indent your code and you start putting things inside other blocks, your curly brackets can start to attack you, and that causes a lot of frustration and pain at compile time. So anyway, this is out there as a reference. If it's useful, great. If not, you know, hopefully you haven't spent too much time on it. It's filled with typos. You can let me know when you find typos. I'll go back at some point and correct those maybe. But, you know, just kind of for what it's worth, it's a free PDF. Feel free to have a look at it. And I think it's more useful as we get into CSE222 in winter, the data structures course. But some of the stuff is topical to what we're doing now, so just wanted to mention that as a resource. All right. Let's dig a little further into this char star business. Hold on, I'm gonna close my window. All right, that's slightly quieter. Let's dig into this char star business, and I want to do this through GDB. So we're going to spend a lot of time eventually talking about GDB. This is kind of a first foray into it. GDB is a debugger. It's meant to be a tool that you can use to figure out what's going on with your program. Presumably when your program isn't working the way it's supposed to, and you've stared at the code and you can't figure out what the problem is. So most languages have their own debuggers. Most systems have debuggers. GDB is the standard Linux debugger. It's pretty much always available. It's extremely powerful, but it's also very good at sort of doing what you want and getting out of the way. So it's a really good tool. If you've done Engineering 270, you've used a debugger already, okay? MP Lab has a debugger in it, and when you start executing your code in the simulator, you're using a debugger. So what kinds of things do we do with GDB or with a debugger in general? One big thing we can do is single step our code. We can execute our program one statement at a time. So we can go through line by line in our C code and do one statement, and then after that statement is executed, we can examine the values of variables, or if we like, we can examine memory directly. So okay, this statement should set, number of sticks equal to the new number of sticks. Well, let's execute that one statement. Now let's look at what the number of sticks is. And if it's not what we thought it should be, we found our problem. All right, so we can single step our code. We can examine the values of variables. We can examine the contents of memory. We can also set breakpoints. So if we know that our code is working well, but something goes wrong in this one function, we can set a breakpoint at the beginning of that function. And we can say, okay, go ahead and just run my program, but stop when you get to that function. And when the machine is about to start executing the code in that function, it will come back to us and it will say, okay, we're at the start of the function, what do you want to do? And now we might start single stepping through and examining the values of our variables and so on, and trying to figure out where our bug is. And GDB will work well with C. We can compile our code with a switch, which is -G, and we can actually examine our source code inside the debugger now. And it will show us our code line by line, including our comments and stuff, as it's executing. It's a very friendly environment. We can also use GDB to do direct debugging of assembly language or machine language, and that's where you're really getting down to the low level and seeing what's happening with the ones and zeros that your program has been translated into, and that can be useful sometimes. And there's a lot of other things you can do inside GDB, but these are some of the main things. We can also do what are called watch points, where we watch certain locations in memory and say, if this location changes, stop what you're doing, come back and let us know. And this is useful. For example, you've got a program which is supposed to, you know, run until some condition happens, and your program seems to exit too soon. So something is changing the value of a flag which should not be changed yet, right? But you can put a watch point on that flag, and you can say, okay, this flag is a 0 right now. As soon as it changes to anything else, let me know. And as soon as that happens, debugger comes back and says, hey, this value was a 0, now it's a 12. And you can see exactly where you are in your code, what the values are of different variables and so on, and hopefully figure out what just happened that changed my flag to a 12 when it shouldn't have. So it's a useful debugging tool. It's a very detailed version of just putting a bunch of print statements in your code, basically. All right. So I want to play with GDB this morning and dig into this char ** argv business. All right. And I want to do this by taking advantage of the debugger. So let me pull a window over here. And I have a program I've already written called main, and it's declared with an argc argv. And all it does is declare an integer I and set it equal to 12. And I'm only doing this so that I can put a breakpoint right here and explore what my memory looks like before the program exits. Alright, so I'm going to compile this, and I'm going to use the -G switch to say include debugging information in the final executable. So I'll do my normal gcc-o main.c, but I'll put a -G switch in there. And if I run this, it doesn't appear to do anything. But if I run it inside GDB, I can say GDB main, and now I'm sitting inside this debugger. Alright, so lots of wordage here. Alright, so we start debugging, let me do a list. So that's what my program looks like right now. So I'm going to say break at line 12. Sorry, break at line 4. Alright, so I have a breakpoint at line 4, which means that before it executes this statement I equals 12, it's going to stop executing. And it's going to ask me what I should do. Alright, and I'm going to run this by just saying run. So you run, it starts executing your program, and it gets to line 12 and it says, hey, I hit a breakpoint. This was breakpoint 1 in line main, in a program main. I'm at line 4 of main.c, which is the statement I equals 12. Okay, here's the part I'm interested in. Main is a function, and any time that the debugger stops inside a function, it will show you what the arguments were to that function. Alright, now we think of main as a main program, but remember it is actually a function. It's declared with a return type, which is int. It's got a name, which is main. It's got arguments. In this case, 2 arguments, an integer, and a char ***. Now, who called this? Well, the operating system called this. Bash called it. Right? When you try to execute a program, there's something which makes a call to this function called main. Right? That's how it finds your code and starts executing it. It's a function call. When your main program says return, you go back to whoever called it, right? And in this case it's bash, and whatever integer value I returned, that gets loaded into the $? variable, and then bash comes back to a command line prompt. So this is a genuine function call, and in this case we're sitting inside the function main. And I want to look at these arguments that were passed to main. So there was a first argument was an integer argc, and that was equal to 1. And the second argument, argv, is 7FFF, FFFF, EB, B8. Alright, and remember, argv is a char star star, which means it's a star to a char star. It's a pointer to a character pointer. Alright, so let's make a memory map. And our memory is normally, you know, byte oriented. We have addresses over here and we have the contents, and each address is a separate byte. But I'm going to make some simplifications. First of all, I'm going to stop writing the 0x7FFFFFFF. I'm just going to write those last four characters, EBBH. Okay, so at this location in memory, we should find the thing that argv is pointing to. All right, argv is a pointer. Its value is EBBH. So the thing at that location in memory should be a char star. Should be the thing that argv is pointing to. The other way to think of argv is an array. When we have an array, the value of that thing, of argv in this case, is the address of the first element. So what we find here should be argv bracket 0. Okay, so let's examine the contents of 7FFF, FFFF, EBBH. And what we find there and in the following 4 bytes is 7FFF, FFFF, EDCF. So EDCF. And the way I'm writing this, there's 8 bytes represented here. 64 bits. Why is it 64 bits? Because I'm on a 64-bit machine. If I was on a 32-bit machine, these addresses would only be 32 bits. They would be 4 bytes wide. All right. So this is the contents of EBB8 through EBBF. All right. We'll play with that more in a minute. But the salient point here is argv is an address, and at that address we find another address. Okay? We're told that argv should be pointing to a char star, which means that presumably this thing is a pointer to a character. So let's go ahead and look at EDCF. And let's see what's stored there. And we find this strange string. 6D, 6F, 682F. And at the next locations in memory, we find 69, 6E2F, 65. And at the next location, we find some more stuff and some more stuff. And if you've spent any time looking at memory dumps in hex, you'll probably recognize this looks like printable ASCII. These look like letters and numbers and punctuation. They're all less than 7F. That's a giveaway. And there's some more. And then there's a 6E and finally a 00. So we have reason to believe that these are not just random hexadecimal numbers. They're certainly not memory locations, because our memory locations seem to start with 7FFF, FFFF. Right? So let's go back and look at the contents of memory, but instead of looking at it in hex, let's look at it as a character. And what we find in that first location in memory, this is at location EDCF, is a slash. And if we look at the next location, that's the ASCII code for an H, followed by an O, followed by an M, followed by an E. Slash NICK slash work2 slash main and an all terminator. All right. And that is argv bracket 0 as a string. It's the name of our main program. And if you look way back here when we started all of this, it says starting program slash home slash nick slash work2 slash main. That's what's in argv bracket 0. And how do we get to it when we're the CPU? We look at argv, that's this number, that's a location in memory. At that location in memory we find another location, and at this location we find the first character of our argument, the slash, followed by HOME slash NICK, etc., followed by a null terminator. All right, so that's the first example. Let me do this again with more arguments, and this will either make more or less sense. And this is not something that's going to be on the midterm. Okay, this is not something that I'm expecting you to make perfect peace with right now. For a lot of us, this is a first exposure to looking at this level of a program, right? But this is where eventually we're going to spend a lot of our time. And when we get into data structure, CSE222, we're going to spend a lot of time working at this level and drawing memory maps and thinking about how things are organized like this. Because we're going to be basically building structures ourselves that look like this, but a whole lot more complex. Where we're going to say, okay, I want a pointer to memory, and at that location in memory I want to find a pointer to another location, and at that location I want an integer followed by a string followed by a pointer to another one of these structures. And we're going to write code that creates these more complex data structures at runtime and then uses them. And when our code doesn't work, we're going to end up running the debugger and going through and building memory maps and taking apart our data structures and trying to figure out what's going on. And this will be something that you'll encounter more in subsequent courses. And when you get into system programming courses or operating systems courses or cybersecurity courses, right? You'll be doing a lot of this stuff. So so this is really just kind of a first glance at this. So let me run my program again. But let me put some more arguments on it. I'm going to run my main program, but I'm going to give it arguments testing 1, 2, 3. All right. So I'm going to come in here and I'm going to say run testing 1, 2, 3. And it's going to say, I'm already running it. Do I want to start from the beginning? And I'll say yes. And so I'm back to line 4 where I'm setting I equal to 12. And it tells me this time main was called with argc equal to 5. 1, 2, 3, 4, 5 arguments. And argv is EB98. So let's make our memory map. And this is obviously just a portion of our memory map, right? Our memory is, however many gigabytes of memory we have on our system, but we're looking at a portion of it. So EB98 is the value of argv. Okay, that should be the char star to which argv is pointing. So let's examine. I'm going to say examine 4 bytes at a time. That's what the W says. let's examine that location in memory. And it looks like 7FFF, FFFF, ED, C1. Now that's an 8-byte address. It starts at EB98, 99, 9A, 9B. This is 9C, 9D, 9E, 9F. The next location in memory is EBA0. And if we examine that location, EBA0, and the following one, it's 7FFF, EDD7. And the next location will be EBA8. And at EBA8, we find 7FFF, EDDF. And the next location will be EBB0. And there we find a 7FFF, EDE1. And the next 64 bits in memory are at location EBB8. And at that spot we find 7FFF, EDE3. And the following location in memory contains 64 bits of 0. Alright, so let's take a breath. argv was all of this stuff. EB98, right? We knew that because GDB tells us when we're inside a function what the value of argv is. But I can also just say print argv, and it'll show me it's 7FFF EB98. Okay, this is a location in memory. It's a pointer to something. What is it pointing to? It's pointing to a char star, which means this EDC1 should be a pointer to a character. The other way that we interpret char stars is an array of characters, right? So we have reason to believe that this is the address of a string. All right, argv itself was EB98. That's a pointer to a char star, but we can also interpret this as an array of char stars. And how are arrays set up in memory? They're stored one after another after another. If we have an array of ints, we have 4 bytes for the first int, followed immediately by 4 bytes for the second int, 4 bytes for the third int, and so on. If we have an array of characters, there's a byte for the first character, byte for the second, byte for the third, and so on. If we have an array of pointers, our pointers are 8 bytes, so we expect to find 8 bytes for that first pointer in the array, that's argv bracket 0, followed immediately by 8 bytes for the second pointer in the array, that's argv bracket 1, followed by argv bracket 2, argv bracket 3, argv bracket 4, and so on. So these values we pulled out of memory, those are the contents of this argv array. I can also print argv bracket 1, and I see my EDD7 there. And the debugger is smart enough to realize that that thing is actually a location in memory, and what's stored at that is a char star, and the chars that it's pointing to form the word testing. And so the print command, P, actually goes further, and it doesn't just show me this memory address, it shows me what the contents is there. But we don't need that. We can look at these memory locations directly. So I can say examine the character at location EDC1. Oh, that's a 0. Let's look at 1. EDD7. That's argv bracket 1. And the character stored there, the byte stored there, is hex code 84. That's the uppercase letter T, followed by E, S, T, I, N, G, and a null terminator. So we can make another picture of the memory map. And at EDD7, we find the letter T, E, S, T, I, N, G, and a null terminator. And that null terminator was at location ED, DE. I'm looking right here. Right, that's the null terminator. And this next location, EDDF, well, that's where argv bracket 2 points. So argv bracket 1 was pointing right here. Argv bracket 2 is pointing right here. And what do we find in that location? We find the ASCII code for 1 followed by a null terminator. And the next location will be EDE1, and that's where argv bracket 3 points. And there we find the ASCII code for 2 followed by a null terminator, and so on. Now in this case, the arguments were stored sequentially in memory. Right, this will be followed by a 3, followed by a null terminator. That's not always the case. Doesn't have to be the case. We can get to each of the arguments by looking at the addresses stored in this argv array. And how do we find those addresses in the argv array? All we need to know is where the array begins. And that's the value of argv that was passed to main. So this one address gets us all of those arguments. Right? But it gets them in this kind of indirect way where we take this, we look at that location in memory, that's the address of the first character of the first argument. If we go 8 bytes beyond that, that's the address of the second argument. If we go 8 bytes beyond that, that's the address of the third argument, and so on. Alright, so this may feel kind of academic, like we don't really need to do this, and we don't. Right? When we're writing C code, we just say, you know, see if argv bracket 1 is an integer, right? And we just pass that to scanf and so on and so forth. But how do those things work? How does scanf actually get to this first command line argument using argv bracket 1? This is how. Okay. So we just want to kind of keep that in mind, and we'll do more with this later on in this course, but we'll come back down to this level a lot in 222. And once you understand the machine at this level, you can do anything you want, right? Once you can think of memory in these terms, and you understand pointers like this, right, you'll never feel squeamish about pointers again. And if you've done 270, this is all indirect memory addressing. Right, you could take this, load it into INDF0, into FSR0, and then INDF0 would give us this location. And you could load that into FSR1, and then INDF1 would give us the first letter of that argument. And then if you iterated the W register from 0 on up, you could use plus W1 to get to each of these arguments until plus W1 was equal to 0, and you've hit the end of the string. So the code related to this is pretty simple. The conceptualization of it is very complex, especially at first. All right, we are out of time there. So tomorrow I want to go back to talking about breaking up code into pieces. I want to start moving towards makefiles and looking at ways we can systematically take these pieces and describe how they get put together into a main program. So we'll play with that tomorrow. All right, thanks. Have a good afternoon.